The identifiability report card says salt is identifiable, garlic is identifiable, the or pear is not. For the identifiable ingredients, the taster proceeds. Now, how much salt is actually in the sauce? Approximate Bayesian Computation (ABC) works by guess and compare. Guess a set of ingredient amounts. Simulate a sauce with those amounts. Run the forward model. Taste the simulated sauce and compare it to the real one using a distance metric. If the simulated sauce is close enough to the real sauce, keep the guess as a plausible recipe. If it's too different, discard the guess. After many rounds of propose, simulate, and compare, the collection of kept guesses forms a distribution of plausible recipes, the approximate posterior. The workflow in practice. Start with a prior. Salt is between 0 and 5 teaspoons. You have no idea. Anything is possible. Propose a value 2 teaspoons. Simulate. Make a sauce with 2 teaspoons of salt. Taste and compare. The simulation is saltier than the real sauce. Reject. Propose 1.5 teaspoons. Closer. Accept. Propose 1.3. Even closer. Accept. After 1,000 rounds, the accepted salt values cluster between 1.2 and 1.7. That's the posterior for salt. PyABC uses sequential Monte Carlo (SMC) to make this efficient. Instead of random guessing, it evolves a population of particles, parameter guesses, through generations. Generation 1, wide tolerance, accept anything vaguely sauce-like. Many guesses survive. Generation 2, tighten the tolerance. Only better matching guesses survive. Generation 3, even tighter. Each generation narrows the distribution, concentrating on the most plausible recipes. The final generation's surviving particles represent the posterior distribution. Why use ABC instead of standard Bayesian inference? Because the likelihood function, the probability of observing this exact taste given these exact ingredients, is intractable for complex models. Your QSP model has 14 coupled ODEs. Computing the exact probability of the observed data given the parameters would require integrating over all possible noise realizations, mathematically impossible. PyABC sidesteps this entirely. It just simulates and compares. If the simulation matches the data, the parameters are plausible. No likelihood function needed. The critical warning. SIAN flagged the 2 herbs, oregano and marjoram, as non-identifiable. What happens if you ignore this and run PyABC anyway? PyABC will converge. It will produce a posterior distribution for oregano, 1.8 teaspoons, credible interval 1.5 to 2.1. These numbers look confident, but they're meaningless. The algorithm found one of infinitely many equivalent oregano-marjoram combinations and reported it as the answer. A different random seed would give different values, equally confident, equally meaningless. The SIAN check prevents this false confidence. SIAN asks, can you determine this ingredient from the output? A structural question about the model, independent of data. PyABC asks, given that you can determine it, what is the actual value? A computational question requiring data. Run them in order. Always. Your GBM QSP model, SIAN flagged 3 non-identifiable parameters. Running PyABC on those parameters would produce confident, but illusory posteriors. The identifiability check is the gate that must be passed before the estimation begins.